Okay, so sorry I'm not there today to do this in person, but we're just going to do a little bit of a follow-up to the atom model stuff that we've been doing. In the comments that you left in your surveys yesterday, some people did indicate that they would like a little bit of a, I don't know, comprehensive. These are some of the details of it. So I'm just going to touch on a few little tidbits of information. So as you're watching this video, you should be taking notes on a few of these things. I'm going to, talk about mass of the particles, charge of particles, and some other things dealing with atoms. It's kind of a summarizing of the things that we learned. So to begin with, we had our different scientists that we researched. Of course, we did Thomson at the very beginning, and Thomson created Thomson's model. And then we had Millikan, who defines the properties of the electron, which as far as properties of the electron, we'll get into mass and charge of that here in a little bit. And then we get Rutherford and Rutherford's model, and his big contribution is that the atom is mostly empty space. With a dense nucleus of positive charge. And then Moseley comes along and discovers the existence of the protons in the nucleus. And then we have Chadwick. He discovers the neutrons in the nucleus. And then finally we get Bohr and Bohr's model, and he finds that the electrons are in quantized energy orbits. And quantize, again, or quantum of something, or quanta means specific. So each energy level in the atom has a specific amount of energy. The electrons exist in that specific orbit. They can jump between orbits if they absorb energy, but then they will collapse back down to their original orbitals and then give off energy. And we'll talk about that a little bit more here in a minute. As far as properties of the different particles are concerned, we'll start with the electron because that's what was discovered first. So we have the electron, and as far as the mass of an electron is concerned, the mass of an electron in kilograms is 9.1 times 10 to the negative 31st kilograms. So it's a very small mass. Charge, and charge in coulombs, is negative 1.6 times 10 to the negative 19th coulombs. As far as protons are concerned, the mass of a proton is quite a bit larger than that of a electron. It is 1.7 times 10 to the negative 27th kilograms. As far as the charge is concerned, it is the same as the electron, only positive, 1.6 times 10 to the negative 19th coulombs. Now, as far as the significance and the difference of the proton and electron mass, just as a little aside here, let's divide the mass of a proton by the mass of an electron and see how much larger it is. So 1.7 times 10 to the negative 27th kilograms for a proton, 9.1 times 10 to the negative 31st kilograms for an electron. And grab my calculator here. 1.7 times 10 to the negative 27th divided by 9.1 times 10 to the negative 31st. And the mass of the proton is 1,868 times greater for a proton compared to an electron. So when we were talking about Thomson's model and the idea that the electrons would account for all of the mass seen for an atom, that's why I said it would take thousands of electrons. I mean, here for a hydrogen atom, it only has a single proton in the nucleus. You would need this many electrons to account for that mass. So protons are quite a bit bigger than electrons in terms of mass, but they have the same charge to them. And then we get the neutron. Neutron mass is 1.67 or 1.7 times 10 to the negative 27th. Now, in the presentations yesterday, and for the people who did Chadwick, they did say that there is a slight difference in the mass. We're only looking at 2 sig figs here. If we carried it out to many more sig figs, then we would see that there is a bit of a difference. So the neutron mass, if we went to 4 sig figs, is 1.674 times 10 to the negative 27th, and for the proton, it's 1.672. So there is a small variation in their mass, but for most purposes, we consider their masses to be equal to make the math easier. And then as far as their charge, they have no charge. Because of the values here, when we talk about the mass of an atom, we neglect the mass of the electrons because they're so insignificant. And instead, we assign atomic mass units. As far as mass is concerned for the proton and the neutron, the proton is 1 atomic mass unit, and because the neutron has roughly the same mass, we also say it has a mass of 1 in atomic mass units. Again, ignoring the electron. I mean, measuring the mass of the atom, including the mass of the electrons, would be like measuring your weight, then plucking a hair off your head, and then measuring your weight again. No scale is going to really detect it. So we just ignore the mass of the electrons. And then as far as the charge of these two, because they are the same but opposite, we just call the charge of the electron -1 and the charge of the proton +1 to once again make things a little bit easier and nicer to work with. Now, as far as the mass is concerned, we use the mass to get the mass of different atoms, and I'm just going to pick on hydrogen. As far as hydrogen atoms are concerned, hydrogen atoms have 1 proton in the nucleus. So the proton, there's your nucleus, and then we have an orbit out here where there is an electron. And so when we assign mass to this hydrogen atom, we count up the number of protons and neutrons, and we get what's called the mass number for this atom. That's equal to the number of protons plus neutrons, which for this one is 1. But that's not the only hydrogen atom that exists. There are a couple of other hydrogen atom types that exist. There's one that has a proton and a neutron in the nucleus, and then it still has a single electron out here. This one has a different mass number though because of that neutron there. This mass number would be 2 because we have a proton and a neutron. They're both considered hydrogen atoms, though, because of the number of protons. And this brings us to something else that came up in our presentations, was the atomic number. The atomic number being the number of protons in a nucleus, and that is unique for each element. Meaning that if hydrogen has one proton in the nucleus, if something else had two protons in the nucleus, it's no longer hydrogen, it's a different element. In that case, it would be helium. So on the periodic table, when you see the atomic number, it's the whole number, the one up on the wall, it's in the upper right-hand corner. It tells you how many protons there are in the nucleus, and that's the defining factor for identifying elements. So both of these atoms up here are hydrogen atoms. One has a mass number of 1, one has a mass number of 2. And then there is a third one, which has a proton, a neutron, and then another neutron. And once again, has the electron out here. But this one has a mass number of 3, 1 proton, 2 neutrons. So the difference between these 3 hydrogen atoms then is the number of neutrons in the nucleus. When we look at elements and the fact that they can have atoms, same type of atom, same element, but different numbers of neutrons in the nucleus, this is when we start talking about isotopes. Of elements. When we're talking about isotopes, we have a single element with atoms with nucleus is, I don't know if it's nuclei, it's probably supposed to be nuclei, whatever. I don't feel good today, so we'll call it nucleuses. Single element with atoms with nucleuses with different neutrons in the nucleus. So here we have, because of the fact that we have one proton in each of these atoms, they're all hydrogen, but they each contain different numbers of neutrons, so they are therefore isotopes of the same element. And when we write the distinction between these, we use something called nuclear notation. Nuclear notation has 3 parts to it. We start with the atomic symbol, and then we write the mass number as a superscript to the left. So this is mass number, and then down here as a subscript on the left, we have the atomic number. And so if we wrote our nuclear notations to distinguish these 3 isotopes, we would have hydrogen 2 here and hydrogen 3 because of the mass numbers. But each of them has a subscript here of 1, distinguishing it that it is in fact hydrogen. Okay, the symbol does that too, but the atomic number again tells us how many protons. So because of the way it's set up, since the mass number is how many protons and neutrons, we can subtract these 2 numbers and get the number of neutrons from it. So mass number 3, atomic number of 1, that tells us that there's 2 neutrons in that nucleus. How these varying isotopes that exist for all different elements affect samples of those elements is what we're going to talk about tomorrow when we talk about mass spectroscopy. Okay. The last thing I want to talk about real briefly then is this idea of the energy levels that exist within atoms. So I'm going to do a little ladder presentation. So this is for Bohr's model of the atom. We have the first energy level, and we'll say that there's an electron here. And this will be the second, and this will be the third energy level. We can, based on equations developed by a couple of different scientists, we can figure out the energy change and thus the radiation that gets emitted for electrons using Bohr's model, jumping between these things. So as I said in class, this electron, if this was hydrogen, sits in the lowest energy level. But if some energy comes in, it can jump up to, say, the third energy level. And when it jumps up there, it could then come back down to its original energy level. And when it does that, it has to give off some energy. And the energy that it gives off is in the form of radiation. Remember, we talked about radiation is energy given off via electromagnetic waves. So we get wave being produced, goes out. Maybe it's in the visible spectrum, maybe it is not. Could be infrared, could be ultraviolet, but it gives off the radiation. So the energy that comes in has to be equal to the energy that leaves, and we can use a couple of different ideas in order to figure this out. So there's really two equations that we need, two ideas. And one of them comes from quantum mechanics and the idea of light as a photon. A photon is basically a packet, or here's this word again, quanta of energy. So again, a defined amount of energy, a specific value. Okay, a packet or quanta of energy that behaves like a wave. So we have this thing, this packet, which is more like a particle, but it's light, so it's only energy, it has no mass. But we have a particle that's behaving like a wave. And in terms of classical physics and chemistry, the idea of particles behaving like waves or wave things behaving like particles is quite contradictory. They don't act like each other. They don't exhibit the same behaviors. But it was Einstein who showed and won his Nobel Prize for that, in fact, light can behave as a particle and as a wave, and he comes up with this idea of a photon. To find the energy of a photon, it's a simple equation. Energy equals H times F, where F is the frequency of the wave slash photon, and H is known as Planck's constant. Planck was another physicist at this day and time, and he develops this equation for measuring its energy. Okay. So if we know the frequency, if we know Planck's constant because it's constant, we can get the energy. Problem is that we have to be able to measure something, and what we typically measure is the wavelength of light. You know, if we're looking at visible light, we'd be looking at the wavelength of light. So there's two other equations that we need. One is called the Rydberg equation. The Rydberg equation is 1 over the wavelength equals what's known as Rydberg's constant, which is, let's see here, 1.097 times 10 to the 7th power. Make sure I'm getting the right value here. Yep. And then in brackets, we have to account for the change in energy levels. And so what we have is 1 over n1 squared minus 1 over n2 squared. n1 and n2, n is the energy level. So if we look at our example up here, we're jumping from the third energy level down to the first energy level. So if we plug in some stuff here, we can find the inverse of the wave length of this thing. So we have 1.097 times 10 to the 7th, 1 over 3 squared minus 1 over 1 squared, which is just going to be 1. And so what do we have here? We have 1 over 9 minus 1. And then we're going to times that by 1.097 times 10 to the 7th. And we get a very large negative number, negative 975,000. And the units here are going to be inverse meters. Now that might seem like a rather large number, but we need to take this and get it back up into Planck's equation. So I'm going to just erase this stuff now since we're done with it. And notice we had frequency in the equation, but when we're talking about light, speed of light is equal to the frequency times the wavelength. Or if we rearrange it, the frequency is equal to the speed of light over the wavelength, or the inverse of the wavelength. So we can use Planck's equation then and this substitution to get that for us. So Planck's constant is, again, we're looking for the energy given off by this photon, this radiation. 6.6 times 10 to the negative 34th. And that's going to be being multiplied by the speed of light, which is 3 times 10 to the 8th meters per second. And since we had the inverse of wavelength here, we don't need to divide by it, we just need to multiply by it. So we've got Planck's constant, we got the speed of light, and then over here we have the inverse of wavelength. So negative 975,000. And what do we get? 6.6, 10 to the negative 34th times 3, 10 to the 8th times negative 975,000. And the energy given off in that transition is equal to negative 1.9 times 10 to the negative 18th joules, which is the unit of energy. So, am I going to ask you to do this calculation in the future? No. But it does get at how we can then define why we saw those spectral lines when we were making the observations with the diffraction gratings. We got specific quanta, this is a quanta, specific amount of energy. That electron, to make that transition, had to absorb that much energy and then emit that much energy to drop back down, and then we would pick that up as either infrared, visible, or ultraviolet radiation. So stepping stones through Bohr's model, a little background in quantum mechanics. It's interesting stuff if you get into it. Anyways, tomorrow we'll talk about mass spectroscopy and how we can then get the masses for the different elements, which is something we've talked about in the past. And see you tomorrow.